Hello and welcome to our presentation on automating audit with policy inference. Modern organizations and systems such as the e-commerce websites, healthcare systems, banking and financial systems, online social networks, etc. are huge applications that handle large amounts of confidential user data. It is no secret that the security of this data has been heavily compromised in the recent years, as not all checks relevant to the security policies are appropriately enforced in the code base. Various factors affect the enforcement of policies in large systems, like constant modification of the policies, their complexities, the enormous size of the code base, and the evolution of this code base over time. All of these factors make it difficult for the developer to ensure that the security policies are correctly implemented at all required places in the code base. Additionally, most organizations may not have an explicit mechanized policy specification, leaving the developers to interpret the policy to implement when specified a policy in English. Developers add inline checks in accordance with their interpretation of this policy, but this is not foolproof. They may accidentally miss some of these checks or implement a less stricter version of the policy, all of which might result in missed authorization checks and security bugs. So most organizations adopt and are also required by law to audit the transactions and interactions of the users with their systems. So the idea here is to log different operations that are performed on the system and then perform an after-the-fact validation of those transactions. The primary objective is to identify all violations of the organization policy and the law. So these organizations normally employ a human auditor or a privacy champion for interpreting these English policies and laws and identifying the violations of these policies in the logs. Given the sheer volume of the log entries, this approach is costly, cumbersome, and time-consuming, apart from being error-prone. So in this work, we base our approach on the insight that the information present in the audit logs, when combined with the decisions that are made by an auditor, is in most cases sufficient to reconstruct a correct mechanized policy. If incremental portions of this policy can be audited with approximately as much effort as the log entries they are generated from, then the cost of manual audit can be reduced over time as more of this mechanized policy is inferred. Based on this insight, we present an approach for automating the audit process by inferring access policies from the log entries. Our approach does not require any prior policy specification. The logs normally contain enough information for the auditor to determine whether a transaction is correct or not. And we leverage this information to generate a partial policy which can subsequently be applied to audit the future log entries. As the policy is constructed, the auditor validates each new policy fragment instead of validating the individual log entries from which they are generated. Entries that cannot be resolved using the information can be logged for further manual review. We show that the number of entries of these policy fragments is significantly lower than the number of log entries that the auditor has to validate. Moreover, the mechanized policy that our algorithm generates can be used to enforce runtime policy compliance, assisting or replacing the inline policy checks wherever appropriate. This figure shows the policy and inference audit framework. A framework builds a policy from scratch given a list of log entries while assisting in the audit of those entries. So the workflow starts with a set of logs and a possibly empty set of policy, which is input to the policy checker and generated. For all entries in the log, the policy checker checks if the entry satisfying an existing formula is in the policy or not. If it satisfies a formula, they are accepted as valid. If the entry does not satisfy a formula in the policy, it generates new policies for such entries and logs the entries in separate review log. An oracle then reviews the set of generated formulas and decides which of these formulas are allowed as part of the policy and which of these are possible violations. The oracle is a function that takes a policy and returns a valid policy. The review logs are then checked against the oracle approved policy, and the violations are then reported for further review. The approved policy is then fed back to the system and becomes part of the existing policy that the policy checker takes as input. So given a list of log entries, an existing policy, a typing environment containing the types of different data items, and a set of relations from the relational database R, the function generate returns the inferred policy and a map which is a map and a map M, which is a mapping from a formula to a set of original formulas. We explain its purpose in a bit. So generate starts by inferring a formula for every log entry in L using infer. This function generates a formula for every log entry by combining atomic predicates from this set of relations. For example, who the owner is, what the relationship of the user and the owner of the data is, and so on. It then reduces this set of formulas using the function reduce to generate a less stricter version of the formula that satisfies all of the existing formulas. That is, if you have two formulas, let's say S1 and S2, then if S1 is a more stricter version of the formula S2, the function returns true and adds a mapping from S2 to S1 in M, the map M, indicating that S2 is the formula that is inferred for log entries corresponding to both S1 and S2. This map is useful when validating the transaction using the oracle. So the oracle takes as input the inferred policy and the map M and generates an approved policy. The isValid function is an abstract function that differs based on the type of the oracle. So if an inferred formula S is valid, it is added to the set of approved policy. If the formula S is not valid, then the formulas that were reduced to S are extracted from the map M, all of which are then checked for validity by the oracle. And based on which of these formulas are valid, some of them are added to the approved policy. So for our inference algorithm, we prove certain properties. So we show that our algorithm is monotonic, terminates, it is sound, and produces a minimal policy. That is, for a fixed set of relations, more entries added to the log will result only in a more or equally permissive policy. And the policy that is inferred by our log is the minimal policy that the log satisfies. So we've implemented our algorithm in Python, where the log is modeled as a table in the database along with various attributes of the data. We assume that only one resource is accessed per entry and there are fixed set of attributes and relationships between the data and various principles in the system. And we employ a human oracle for validation. For experimentation, we generate stimulated logs for a healthcare organization based on the HIPAA privacy law from prior work from Garg et al. So we measure the time taken and the number of formulas input for various number of log entries, and an important result of this experiment is to show that the saturation of formulas generated over time happens as new log entries are added to the log. So in this experiment, the number of input formulas quickly stabilize once 50,000 log entries are processed, and for 350,000 log entries, the number of input formulas is just 400, which is less than 400, which the auditor has to validate. To summarize, we present an approach for automating the auditing process by inferring access policies from log entries without requiring any prior policy specification. So this significantly reduces the efforts that are required by an auditor to detect violations, thereby reducing the time required and errors in auditing. Additionally, the mechanized policy can be used to enforce runtime policy compliance, replacing inline policy checks wherever appropriate. Thank you.